Okay, all right. So thanks everybody for coming. Welcome to one more session. I realize that semester fatigue has reached uh, almost critical levels. That is what I can tell by the number of people who have shown up today. So I thank all of you for coming, and despite, um, well, whatever, despite everything, you're here. So thanks for coming. Okay, so today is our 21st, 22nd class. So online class number 22, September 30th, 2020. Okay, so before I begin, let me ask, are there questions about what we have covered in the last class or in previous classes? Okay, well, as always, you can always unmute yourself and ask a question at any point in time. You can put a question in the chat. You can, I forgot to share the YouTube link, but I think people can find the YouTube link from just by going to my channel on YouTube. I'll share it in. Okay. Please put that on WhatsApp. Okay. All right. So please ask whatever any doubts that you might have. Let me in the meantime, I will summarize what we talked about last time. Right? So the goal is that we want to talk about how to connect all of these techniques we have discussed so far, which apply to discrete quantum systems, to things like the free particle. And the free particle, for example, is described by something we all know, which is called the Schrodinger equation. So today I will also talk about what the Schrodinger equation is. And so we have this concept that if you start from a discrete quantum system and you consider a larger system made up of several discrete systems, the dimensionality of your Hilbert space increases very rapidly. So even as something as small as having 10 spin 1/2 particles has a dimensionality, Hilbert space dimensionality of 1024. What that means is that your matrices, your operators are 1024 by 1024 in size, and your state vectors have 1024 components, right? So that's a lot of information, right? So you can imagine as you go up to 10, 20 or 30 or 1 mole of particles or atoms, the size of a Hilbert space becomes infinite for all practical purposes. So what we have in that case is we have to understand how to describe a system with an infinite number of degrees of freedom. So an example of such a system is what is known as a particle in a box, right? And a particle in a box can be constructed in several ways. Let me give you an idea of how such a system looks like experimentally, right, in the laboratory. It's easy to talk about such things theoretically, but we should also have an understanding of how they actually work. So imagine that you have a straight wire, and on 2 points along this wire, you connect two potential sources like this. So two you connect both of these points to the negative terminal of some battery. Okay, so you have some battery here. So what this will do is, this will, so then, okay, let's say this is ground or something. So then what this will do is, relative to the zero of the potential. So here what you would have is, you would have zero potential in these regions, right? And at this point, what would happen is, you would have a negative potential, right? At this point. So here V would be something, let's say minus V naught. Okay. Now, this is a wire. It's a metallic. It's a, well, it doesn't have to be a metal. In fact, maybe it's better not to use something metallic. Let's say it's made of some sort of non-conducting fiber, but you inject a single electron into this wire. Okay. So you inject it. There is some, either you shoot the electron or have some deposited in some way on that segment. What will this electron experience? This electron will, when it is in this region over here between these two terminals, so let's call this region point A and point B. When it is away from these terminals, right, the electron will not feel any force, right? So effectively, when it is away from these terminals in this region, let's say, here the electron does not feel any force, and we can say that the potential is zero. Now keep in mind, it's important to keep in mind that in when we talk about potentials, it does not matter what your absolute value of a potential is, right? Absolute values of potentials don't matter. They don't have physical significance, right? What matters is the rate of change of your potential as a function of distance, right? So if you have a potential, some function v of x, and then we can say that a particle will feel a force which will be a function of x, which will be given by, so some charge of the particle with a negative, there'll be a negative sign, negative, the gradient of this potential, right? So what matters is how the potential changes from point to point. So we could also take this potential here, instead of zero, we could take it to be some non-zero quantity. But the main thing is that the potential here in this region is a constant. So if I want to make a plot of this, I can make a schematic plot just to show this is the potential in the region outside the well. Now, as you come close to these terminals, what happens? Let me move this a little bit down here. So this is the potential outside this region. As you come close to this point A, what happens is your potential drops, right? So the potential of this point A relative to the potential outside is negative. So your potential drops, right? But again, as you are inside the region, the potential again, it stops changing. So inside the region, again, it's a constant, right? So it looks like this. This is what your potential function is as a function of position. So this is position, and this vertical is your potential. Okay. So what happens to this electron? Well, the electron, if it is inside this region to begin with, right? It doesn't feel a force when it is here, when it is away from the edges. It doesn't feel a force, right? Because the potential is flat. But as soon as it reaches the near the edges, right? So near the edges, what happens? Near the edge, the potential starts changing, right? If you zoom in, if you zoom into this region, right, you will see that the potential starts changing. It won't be exactly like a step. And so as the potential starts changing in this region, what happens? The electron feels a force. And which direction does it feel a force? It feels a force pushing it away from this point. The same way, if you are on the other end of this segment, again the electron will feel a force as you reach in this region. Why? Because now the potential is changing, and the force will tend to push the electron away from this point. So this is point A and point B to make contact with our picture over here. Let me put this right. So the electron effectively is trapped within this one-dimensional region, right? If you want the electron to jump out of this region and go over here, what do you need? You need to give the electron a certain amount of energy, right? How much energy do you need to give the electron? You need to give it an energy which is equal to delta E is equal to the charge of the electron times the height of this potential. And the height of this potential is determined by this value V naught, right? Is it clear? I hope this picture is clear. If there are any questions, you please ask me. Right? So effectively, this means that the electron is trapped in region 1. We will call this region 1. So this is region 1. We'll call this region 2 and call this region 3. Right? Now what I can do is take my potential V naught and I increase it. Okay? So the absolute value of V naught, and I take that to infinity, let's say. Okay, just hypothetically speaking. So as you take it to infinity, what happens? The amount of energy required for the electron to escape the box also goes to infinity. So this is the escape energy. So then what happens? Electron can never escape. From the box. And this is what we call a particle in a box. Okay? So even if the potential is not infinite, it's still a particle in the box. It's just that the walls of the box are permeable. The electron can go through those walls. But if the potential is infinite, then the walls become impermeable. Okay? So we use this Schrodinger equation to describe the behavior of this electron, right? Now, what is the the Schrodinger equation. Let's see. I'm running out of colors to use. For my next heading, what should I use? Doesn't matter. So what is the Schrodinger equation? This is how most quantum mechanics courses actually start out. They start out by telling you what the Schrodinger equation is. I have followed a different approach, and I don't know how effective my approach is. I hope that it is easier than the other approaches, but that's up to you to, you are the judges of that. So the Schrodinger equation has this form. Let me write down and then I will explain the different terms. Okay. So what is this? This is a differential equation. This is a differential equation, right? Because there is a derivative operator here. There is a gradient. This is a spatial gradient. And this is a gradient in time, right? And there is some function psi, and psi is a function of both space and time. It's a function of x and t, right? So what are these various terms now? So let me copy this to the next page. Okay. So these various terms are this term over here, the first term on the left-hand side, is the kinetic energy. The second term, well, what goes along with kinetic? You guessed it, it's the potential energy. Right? And what happens when you take the kinetic and potential and you add them together? You get the total energy. Okay? So we can write this expression as more symbolically as T plus U is equal to E. This is the Schrodinger equation. The kinetic plus the potential is equal to the total energy. Okay? The kinetic plus the potential is also known by a different expression, a different word is used. It's called something called the Hamiltonian. So it's named after whom? It's named after a guy named Hamilton, right? So it's called the Hamiltonian. Now, this whole expression can also be written as H is equal to E. The Hamiltonian is equal to the total energy. Okay, but we have to be a little bit more careful, right? We have to use the terminology of quantum mechanics, right? Because we know that this is what we're talking about is quantum mechanics. So what is this psi of xt? This psi of xt is our state. right? It's a state of your quantum system, right? In fact, what it is it's a vector, right? It's a state vector. And remember, in the previous class, we talked about how if you have a continuous function, such as something like this, the cosine function, for example, this function, it actually represents the components of a vector. And so we should not refer to this as the vector, but we should it is the state vector components. These are the components of the state vector. There is a single component for each point x. Okay. Now, so what about these other things? These other things, if I just ask what is this guy? Well, this guy now becomes an operator. Okay. So why is it an operator? Well, because it takes a function. An operator is anything. An operator is basically a machine, okay, which takes input and gives you some output. In the context of Schrodinger equation and quantum mechanics, so if you have something that's an operator O, what is the input that this takes? The input it takes is some function, okay? And what is the output it gives you? The output is also another function, okay? So as an example, you look at this guy. What is this doing? It's taking your psi, it is calculating the second positional derivative of this psi, and that is the result of your operator, action of your operator. Okay. Now, what about this guy V of x? So you see there is a slight difference in these two operators. Here, this derivative operator is doing something to this function. You might say that, well, in this term, the V of x is not doing anything, but it is doing something, right? It is multiplying the function and changing its values, right? So V of x is also an operator. So this is the operator for the kinetic energy. And this is the operator for the potential energy, right? And then finally, we have this guy. What is this? This is also an operator, but now it's an operator for the total energy of the system. Okay. So this equation, right? I'm calling this the Schrodinger equation, quotes unquotes. I should be a little bit more careful, right? I should write it in this form. Remember that when we have operators in quantum mechanics, we generally put a hat on top of the character to denote the fact that it's an operator. So you have an operator, which is the Hamiltonian operator. So what is the Hamiltonian operator? It is this guy. right? What is the energy operator? This IH bar d by dt. And together, these two combine to give you the Schrodinger equation. You have to take the Hamiltonian operator and you act on the Hamiltonian operator. You act on the state psi of x t with the Hamiltonian operator on the left hand side, and on the right hand side, you act on it with this total energy operator. And these two are equal to each other. And this guy is called the, so normally what you will see is this expression, h acting on psi of xt equal to IH bar d by dt psi of xt. This is what you will see as, if you look up Schrodinger equation, this is another expression of the Schrodinger equation. So this is identical. This is exactly the same statement as this guy, okay? These two are completely identical. This expression and this expression, they both say exactly the same thing. Only difference is that here we have written the left hand side as a single operator. Okay. Any questions at this point? I'm going to put a nice box here because, well, it deserves its own box. Questions? No questions? Okay, well, I'm done playing around with this box and I can continue. Okay, so this is the Schrodinger equation. This Schrodinger equation applies to all quantum systems. It doesn't matter whether they are discrete or continuous, finite dimensional or infinite dimensional. When you have a continuous system, so the only thing that changes is the form of this operator. When you have a discrete system with a finite number of degrees of freedom, you cannot write the Hamiltonian operator in this way. Why? Because, well, in that case, your state is no longer written as a function of x and t, right? It will be a discrete function. So instead of writing it in this form as psi of x and t, it is better that I write it in this slightly more accurate way, in this way. So this is our Schrodinger equation, right? Now this ket psi, now it looks exactly like what we like and we are familiar with. This is an eigenvalue problem, right? And remember that we in linear algebra, because all quantum mechanics is linear algebra. In linear algebra, the typical sort of problem that you have is that you have some vector, right? And you have some matrix, and then you ask what are the eigenvalues of this matrix, right? This is the eigenvalue problem. Here we have some vector. What is that vector? Ket psi. We have some operator h, and we are saying that this guy acting on this state will give me some eigenvalue. So what will be the eigenvalue? That eigenvalue will be the energy of that state times the state itself. And what is this H? This H is your operator. Now here you will notice that I'm calling this a matrix because, well, it's a matrix. Then the natural question that pops up is the following. How is this a matrix? Right? So we'll come to that at a later point, okay? I think there was some lag in my display and speech. If there is any lag, you please tell me, okay? Let me see YouTube, anything. Some people are watching. There are no questions as usual. Okay. Are there any questions from any of you guys? Somebody please ask me something. Maybe I'll have to start giving out like rewards, Amazon coupons or something like that for questions. Okay. No questions. Are you still there? Is anybody there? Hello.
Yes,
Aditya is there. Thank you. Anybody else?
Yes, sir.
Okay. So nice to hear some voices finally. Have you all seen? Do you know there's a movie called The Sixth Sense? How many of you people know about the movie Sixth Sense? Anybody knows?
no, sir. Heard.
Heard of it, huh? Yeah, you were all probably very small when it came out. It's about a person who is talking to a small boy. Bruce Willis is the actor. You know who Bruce Willis is? I hope, maybe. It's you are all in a different generation entirely. What used to be like movies for me are old-time classics for you. So the Bruce Willis talks to this young boy throughout the movie, and at the end of the movie, we find out that actually the boy has been dead the whole time. He's a ghost. No, not the boy. Sorry, Bruce Willis is the ghost. So the little boy, he sees dead people. So sometimes when I give these Zoom talks, I'm not sure if I'm talking to real people or not. Rakshit Rao, scary. These days movies are a lot more scarier than that. That is, Sixth Sense is actually so nice. You don't find out till the very end that it's that Bruce Willis is actually a ghost. Okay, so any questions now? No questions. Okay. Is that story scarier than quantum mechanics? I don't know. Somebody might say that quantum mechanics is scary, but that's only if you are scared of it. If you approach quantum mechanics with a biscuit and say, here quantum mechanics, here quantum mechanics will wag its tail and come and lick your hand and be your friend. So okay, that's my humor for the day. As always, Zoom humor is completely underappreciated because there's no response. No questions at this point, right? No questions. Everybody understands everything. Okay, wonderful. All right. So we'll come to that. We'll come to this. We'll come to that eventually. Okay? I'll come to that eventually. For now, you just believe me when I tell you that these two expressions are the same, saying the same thing. Okay, so now let's see. How does any of this help us? Okay, what is this equation actually telling us? What is the physics it describes? So we have learned how to describe a quantum system, the state of a quantum system, but we have not yet talked about how the quantum system evolves over time. How does the state of the system change over time? So this equation tells us how a quantum state evolves over time. Okay, so this is the expression of dynamics. This is where things actually happen. Okay, so without this equation, we would not be able to do a lot with quantum mechanics, because it's not enough to know what a system looks like at a certain instant of time. You have to describe how a system evolves over time. Another thing you need to be able to do is you need to be able to describe how systems interact with each other. So, for example, if I go back to this particle in a box, instead of one electron, I can imagine that there are two electrons. Now, those two electrons will also have some force between, they will exert a force on each other. And so then the question becomes, and the state of that quantum system will be the state of two electrons instead of one electron. So then the question will become, how do I describe the evolution of that combined state and how that evolution is affected by the interaction between electrons? So all of that is actually encoded within this potential energy function. So if you put in second electron, what will happen is the first electron will feel a change in its potential energy due to the presence of the second electron. And so when you write down the Hamiltonian, this Schrodinger equation for the whole system, you will have to include that contribution from the electron-electron potential energy within this potential term. So this guy, this H, this describes everything. This describes the possible energy values of the system, the possible states it can take, the possible interactions of the system within the system. It also describes how, if you have some external stimulus. So for example, you can imagine that now you send in a photon. Okay, and you want to ask, well, what does this photon do to this electron? Right? So the electron is trapped in a box. When you have the electron trapped, you can do experiments with it. You can apply an electric field. You can apply, well, you're already applying electric field, but you can apply an external magnetic field to it. You can send in a photon from outside. You can send in, and see what happens to that system. All of those effects will be captured by this potential function. Okay. All right. So now let me wrap up by showing you how to solve this Schrodinger equation. Okay. And the solution is actually not very difficult. Let's see what happens. Let's assume that H, the Hamiltonian, is time independent. Okay. What that means is that this term is already time independent, right? There is no time variable here. But this potential, this external potential term, it can, in general, it can be a function of time, right? As an example, you consider a photon which comes into the system interacts with the electron and then leaves. So the potential of that system, or potential energy of that electron will be changed, but it will only be affected during the period of interaction, right? For a finite amount of time. So the potential V of X will become a function of time during that a period of interaction. So here we assume that V is only a function of position. Okay. So then we can give a very simple solution of this equation. What is that solution? First, let me write something else. Okay, a little bit different. Let's say that I have some function f. Okay. So let f be a function. Okay. And now let's see, we have some operator A which acts on this function. Okay. And it gives us IH bar df by dt. Okay. But now I don't need to write this partial, I can write it as a total derivative. And now if you look at this, you can rearrange this equation a little bit. You can write this equation in this form. You can put dt on one side, on the other side you can put, or actually on one side we'll put dt divided by IH bar. On the other side we'll put df divided by A times f. Okay. Now this can also be written as minus I over h bar dt is equal to 1 by A times df by f. Okay. For the time being, just imagine that A is some constant. Okay. Now I can integrate both of these sides. When I integrate both of these sides, what do I get? On the left, I get minus I by h bar t minus t naught. On the right, what do I get? I get 1 by A log of f minus log of f naught. And this can be written, right? This is a very simple integral. You all, I'm sure, have done these integrals many times before. So this can be written as log of f by f naught. Okay. So now this expression becomes log of f by f naught is equal to minus I over h bar A times t minus t naught. Okay. And we can set our initial time to be 0. We can always, make a choice. It doesn't cost us anything. And then we can take the exponential of both sides. And what do we find? We find that f of t, right? F is a function of time now, is equal to f of f naught times exponential minus I by h bar at. Right? That is the solution of this equation, right? Okay. In fact, I didn't have to take this A down here. It's better to just leave it up here. So do a little bit of surgery here and just put A here. And because my assumption is that this A does not depend on, in our case, what does this A correspond to? It corresponds to this Hamiltonian. And since this Hamiltonian doesn't depend on time, I can keep it outside the integral. Okay. So let me write this again, but now in terms of the state, psi as a function of time is equal to exponent. Now I'm going to write things a little bit differently. Xt psi naught. And this guy, this is the solution of the Schrodinger equation, the time-dependent Schrodinger equation. It tells me how my state changes with time. Okay. So now there are a couple of things to keep in mind. Psi here, this is the state at the initial time. This is a state at some later time. This guy h, what is this h? This is an operator. You have to remember that this is an operator. Since this is an operator, when you take the exponential of this guy, you will get another operator. Okay. If you take the exponential of a matrix, what happens? You get another matrix, right? Same way, this is an operator. This operator has to sit to the left hand side of the state. That's why I put the state on the right hand side, right? In this expression, I was not very careful about where I put f, because I was just treating f as some ordinary expression and I wasn't treating a as an operator, right? But the purpose of this derivation, this whole derivation, was to show you how to get this final form. And now what I'm telling you is that one can do this derivation rigorously, you know, with operators and states, and you will get exactly this solution. So this is the solution of the Schrodinger equation. And I'll leave it here for now. And then in our next class, we will come back to this. Yes.
Sir, first you consider h as only position vector, right? Then after solving, you get the whole equation in terms of h, which is dependent on t as well. So how the both are...
No. H is not dependent on t. Na? Where is h? Here I have assumed that, see, here I have assumed that h is time independent. Okay. Fine.
Yes, sir.
Now here, this h is again something time independent. So where do you see the time dependence of h coming in?
How the state vector is time dependent, but the h...
The state vector is time dependent. Right, the state vector is time dependent.
Okay,
So,
I have to check it again. I didn't get it.
So this is what the Schrodinger equation tells you, that your Hamiltonian does not have to have any explicit time dependence. Okay, so here your Hamiltonian does not have any explicit or implicit time dependence, but your state vector is still a function of time. See, this is not very surprising. You have the same thing in classical mechanics, right? So actually, in a way, this Hamiltonian, when I say that it's time independent, strictly speaking, it is not completely time independent. Why is that? Okay, because this Hamiltonian, it contains this gradient, right? Now this gradient is a derivative with respect to position. Okay, but what will happen is that you imagine starting off with this state at some instant of time, and then in the next instant of time, delta t, your state changes by some amount, okay? When your state changes by some amount, what happens? The derivatives of that new state will also be different, right? See, the important thing to realize is that an operator, when you say an operator is time dependent, okay? Or time independent. H is time independent, right? But H acting on some state is not time independent. Do you understand this? Yeah, Vijay, you can always leave. You guys can always leave as soon as you have class. That is our understanding. I tend to continue a little bit longer than I should, I suppose. See, because the state is not time independent. And this guy is the action of the Hamiltonian operator on the state. Okay, now the exodus has begun. So, Yukta, is that making any sense to you?
Yes, sir. I got a little bit. I'll read it again then.
So, Preet, did you have a question?
Sir, hello, sir. Sir, how does the wave equation of electron in the potential well similar to this solution you got? Because
It's exactly it is exactly the same. We will talk about how it is the same in future classes.
Okay.
Everything I cannot cover in one class. Otherwise, it will be too much.
Okay.
Sir, excuse me, sir.
Yeah. Go ahead. Ask me a question.
Sir, this whatever you have got the result as a function of time, it's correct only if you don't make any changes to the system, right? Like you don't perform any measurements, you don't collapse the function.
That's right. That's completely correct. That is completely correct.
So, sir, what if I collapse?
Yeah. So if you have a measurement and you
like
have
it's a mixture of.
Right. So that then what will happen is the state will collapse into some eigenstate. Okay. And then what will happen is after that collapse, it will again start evolving.
As a function of this, or will it be different? Like
so it will
now phi naught will change, right?
Right. Psi naught will become the new whatever it collapses into, that will be your psi naught.
Okay, so got it.
And then let's say you continue evolving, and then again it collapses. You make a measurement, again it collapses into some state, that becomes your new psi naught, and then from there it starts evolving again.
So, but if a state is only one eigenvalue, like phi equals some x0, then how will you then there must be no evolution, right?
No, that's not. No, because of this gradient term, right? See,
eigenvalue changes with time. Okay, got it.
No, it changes with position also, right? So you're saying that what if psi is a function, psi is non-zero only at a single point, let's say. If psi is non-zero only at a single point, right? Well, then the derivative will not be non-zero, right? Because if you have a function that looks like this, the derivative of this function is not zero, right? Because the derivative tells you, well, there is some change happening over here. Okay. Yeah, sorry, you were trying to say something. Your voice is breaking up.
got it. Because of that del square term, it will bring an additional term, even though
Exactly.
it's not zero. Yes, I got it.
Okay. You can have a situation
Yes.
where psi is just a constant. Let's say psi is a complete constant as a function of position, right? In that case,
Yes, sir.
this term will be zero.
Oh, okay.
But such a state would correspond to a state of zero energy. And what we will
Sorry,
see
that
is that
last part I didn't get it.
don't worry about it. Okay.
Okay.
Okay. So any other questions?
Sir, is there any derivation for the Schrodinger wave equation?
Yeah, there actually is a derivation. There are many different derivations.
Do you show one, sir?
Not right now. Not right now, but I will talk about not a derivation, but a motivation, like how one can, construct this equation. But there are derivations, but they require us to talk about things which are a little bit off course, quite off course. So, and a little bit more technical also. So, but I will motivate this equation in the next class.
And IH dou by dou T is the energy operator, right?
That's right. So I will motivate the construction of these operators in the next class. Why is this the energy operator? Why is this the moment, this energy, the kinetic energy operator? These I will motivate in the next class. I will explain what it means. Okay.
And momentum operator is minus I dou H by del, right?
Minus IH bar by minus IH bar.
Derivative of position.
That's right.
Can't we combine them into some 4 operator or anything?
Yes, you can. That's called the Dirac equation, and that is completely beyond the the scope of this course. Okay. All right. So I'll stop the record. Yeah. Go ahead. Ask me. Yeah, of course. Please go ahead.
In the previous class, we changed from double integral to single integral. So I got the analogy that like similar to the summation part, but I'm not quite convinced like how the double integral changes to single integral, because the LHS is like it's like multiplying areas, right?
Say that again.
Like the double integral part, we are summing over areas and then multiplying them.
Something like this, right?
Yes, sir.
I see what you mean. You're talking about, okay, when you talk about an integral. Okay,
yes,
so
sir,
let me.
There are two dx and dx prime, but on the RHS there's only dx.
One second. I understand what you mean. So your question is the following: that when I talk about an integral, let's say I1 of some function fx dx, then this integral amounts to calculating the area under this curve, right?
Yes.
I1, and same thing for some other function g also, right?
Yes.
I2 is integral of gx dx, and this is also an area again. This is I2, and so what you're saying is that, well, I'm taking I1 and I2 like this, right?
Yes.
Okay. So now let me tell you why that is not exactly the case. Okay. It is not the case Why? Because of the presence of this delta function.
Okay. So is it like the delta function takes up one dx or something?
So for instance, if I was to write this I1 cross I2, I1 times I2, what would it be? It would be double integral, right? Fx gx prime dx prime, right?
Yeah.
This is what you would get. This would be like, the dimensionality of this would be like area squared. But the thing is that our integral also has a delta function, right?
Yes.
What does the delta function say? So if you look at this expression, fx times gx prime, okay? So this is x, this is f of x, this is g of x prime, and this is x prime, okay? Now, if you look at this function f of x times g of x prime, by the way, if you have to go to class, you can go to class. I can meet up with you guys later if you want to do that. Or do you want me to finish right now?
Continue.
Continue.
Okay. I don't have a class.
Huh?
I don't have a class now. So.
Okay. All right. So now, if you look at this expression here, fx times gx prime, what it means is effectively you're multiplying. If you take one element of x and multiply it with every element of g of x prime, then you take another element of x, f of x, and then multiply it with every element of gx prime, right? That is what is happening in this case, right?
Yes.
But when I include this delta function, then the thing changes. Why? What happens because of this delta function? This delta function tells me that in the integral, all of the x's have to be equal to x prime. Okay. So that means I am not multiplying f of x by g of x prime, but in fact, I'm multiplying f of x times g of x. So I'm taking 1 point here, multiplying it with 1 point here, 1 point here, multiplying it with 1 point here. What I'm doing is I'm superposing these functions on top of each other.
We are multiplying the same points together, right?
Exactly. Give it a different color maybe. So what I'm doing is point-wise multiplication of these functions. Okay. So it is exactly the same as taking a vector in a product. Vector in a product is like this, right? This is a point-wise multiplication. Right? Yes.
Yes.
Same way, if I have two functions, how do I take the inner product of two functions? Assuming that, well, I have to take the point-wise inner product. So that means I take f star g of x. I'm putting this star here because of this notation. So if f is a real function, then it will just be equal to f conjugate will just be equal to f. So the point-wise product of these two functions will be given by an expression of this form, right? This is the product of the two functions at the point x. But there is also a sum, right?
Yes.
There is a sum over all of the products. How do you express that sum in the continuous case, you have to write an integral, right? That is how you sum over a continuous function.
Yes.
So in this case, I took the inner product of this state with itself. I can also take the inner product of two different states. I can take psi of m and take the inner product with psi of n. Now, where does that delta function come from? The delta function comes from, if you remember, this state is written in terms of this ket x. This state is written in terms of ket of x prime. So this is this is bra of x, and this is ket of x prime. And these two states, when I take the inner product of these two guys, I get a delta function because they are orthogonal to each other.
Yeah, we converted the Kronecker delta into a delta function, right?
Into a Dirac delta function. And so this resulting is that you get this pointwise product of these two functions. See, again, this will only start to make more sense once you do some problems and sit down and work through all of this yourself. Okay.
Yes.
So I will share the notes with you guys. Just sit down and work through them step by step at each step. Then that is the only real way to understand what is going on. Okay. Utsav is asking on YouTube, I don't know when he asked, how can two operators act simultaneously? Is it that we take the sum after measuring the effect of the operator? So, well, here, Utsav, I don't know. See, well, two operators are not acting simultaneously. We are saying that on the left-hand side, you have one operator. On the right-hand side, you have another operator. We are saying that the action of this operator is the same as the action of the other operator. So what you are talking about is something different. When you say that two operators acting simultaneously, what it means is something like this. You have an operator A and an operator B. So first the operator B acts on the state, then the operator A acts on the state. This is what I would describe as two operators acting simultaneously. But that is not what is happening in this case. Okay. All right. Okay, so I think I'll end it here. You guys, please, if you have any questions, post them in the Moodle forum. Okay. And what I will do is I will have another session at some point in the afternoon or evening, sometime this week, when you can clarify more of your doubts with me. Okay. Are there any other questions? Well, there's just the two of you are left, so I'm going to end it here. Okay. Okay. All right. So thanks for staying, guys. Thanks for sticking around. Appreciate it.